discuss the following, right? For now, okay, right, this is going to be P plus V squared over 2 plus GZ. Okay, right. So we have this term, okay? So what exactly is it that this term here refers to? This term, it's a way of summarizing the energy content of a mechanical system, okay? That's not the most accurate description. I'm sure there are far more accurate descriptions, but for now, this is the description that we are going to work with, okay? Simply meaning this is an equation that summarizes the energy components of a mechanical system. Now let's go deeper, okay? Let's try to define these components, right? Okay, right. Let's start with this top term over there, okay? That is known as the mass flow rate. Okay, right? Mass flow rate. Okay, and then this over here, this is known as our flow energy. Right, and then this over here, it is known as our kinetic energy. Kinetic energy is normally associated with speed, okay? In this case, velocity or whatever you want to call it, okay? Right. Then our G times Z, Z actually constitutes as height, okay? And then the energy component associated with height, traditionally or conventionally speaking, we refer to that as our potential energy. Right, potential energy, right? Now, why is this important? This is actually critical, and this is the reason why. Let's assume over here that you have your veins or your blades, whatever fancy name you want to give it. Okay, and it's rotating. It's rotating. Okay, right. There's one thing that we have to notice. We have to notice that the region, okay, within which it is rotating, that region, it is not concave, it is not convex, it is parallel. Now, why am I pointing out the fact that it's parallel? The fact that it's parallel, it's a term that's used intentionally. Intentionally, why? Because it is subjected. When I say subjected, let me put it to you like this. Let's say this is P initial, this is P final, okay? Now, first of all, I mean, why not XI, XF, why PI, PF, PF, PI? Because the P is for pressure. Pressure, where do we get this pressure part from? We get the pressure part from the fact that it's what? Atmospheric pressure, okay? And then what we do know about atmospheric pressure is that P final and P initial, it's actually what? The same thing. The same thing. Because atmospheric pressure, it's what? In this case, it's assumed to be constant. That's the design assumption. Okay? Now, why is that the design assumption? Because if it's like that, then obviously your pressure at this point and then your pressure at that point, they cannot be the same thing. Okay? Obviously, if it's like this, your pressure here and then your pressure here, it obviously isn't the same thing. However, if it's like this, then we can agree that your pressure is the same thing. When I say pressure, same thing, I mean P final relative to P initial. Okay? Same thing, right? Now, why is that important? That is important because our flow energy is dependent on what? Pressure. However, there is no change in pressure. Why? P final is the same as P initial. So if I say P final minus P initial, I get 0. And if I get 0, it means my flow energy is what? 0. Okay? Now the same thing happens with our potential energy. Our potential energy, we are looking at it, or we are interpreting it in the context of elevation. Elevation simply means if there's a high point, here's a low point. Okay? When you move from a high point to a low point, that movement, it's a function of potential energy. Okay? It's a function of potential energy. It's the same as if you move from a low point to a high point. I mean, one of the requirements there is what? Potential energy. Okay? Why? Because potential energy, it speaks to a change. It speaks to a variation in elevation. Okay? Simply meaning you want a H initial and a H final. An initial height and a final height, but because this thing, it's stationary, there is no elevation. What happens? Our final height and our initial height, it's the same thing. And because it is the same thing, there is no change in potential energy. Therefore, rendering potential energy what? Zero. Okay? Then we are left over with the following. Okay, we are left over with this term. Now, what is this term? This term, it's essentially the mass flow rate multiplied by what is left. And what is left? It's our kinetic energy component. Okay, this can also either be written. Yeah. Okay, there we go. That's more like it. That looks more familiar. Okay, right. Now, what's happening here? What's happening here is actually something very interesting. Okay, we are obviously not going to catch it, but we are supposed to catch it, meaning we are obligated to catch it. And what are we supposed to catch? The following. Check this out. Now, what is this? This is the equation that describes the mass flow rate. Just as an add-on, this is the units of the equation that describes, or the expression that describes, the mass flow rate. Okay? Now I'm just putting this out there. This is just one of those by the way things. Okay. And since we are at it, we might as well weigh in another add-on. Density is actually equals to pressure, gas constant times time. Okay. This is what the rho, I think, is. Yeah, rho, it's density, yes. Okay. Now, why is that important? That is important because of the following, nah? Now, this is what you get when you substitute this in there. Then you are left with this. Now, why is this important? This is important because of the following reason. Our potential power, let's call it that. Okay, why do I say potential power? Because this is not actual power, it's potential power. Meaning if it's 100% efficient system, then this will be the power that we get out. Obviously, this is not the power we get out, hence it's potential, because it depends on a lot of efficiencies in the system. Okay, right, long story short, so this is our potential power generated by the turbine, and that power, what do we notice? It is a function of area. Another way of defining this area is by saying the radius of the blades on the turbine, but that is a linear relationship. It's a one-to-one relationship. Okay, the thing that actually carries the meat on the bone is the speed. Because if you look at the speed, now let's assume the speed is 1 to the power of 3. It remains 1. It's not a big deal. meaning your multiple is 1. But now let's take it and let's make the speed 2. If you say 2 to the power of 3, you get 8. Oh, your multiple went from 1 to 8. If you just double the power from 1 to 2. Now let's take the power from, let's take the power when the speed goes from 2 to 3. If it's 3 to the power of 3, it's 27. That means your multiple, it goes from 8 to 27. So if your speed is 1 meters per second, 2 meters per second, and subsequently 3 meters per second, your power output, it will go from 1 to 8 to 27. Imagine that. Okay, and that's why this is important. Okay, however, and this is actually what's key. Check this out. Once we have this, what we can also do is the following. We can rewrite it. We can rewrite it like this. Now, why are we rewriting it like this? Because this over here, this term is what we refer to now as the power density of a wind turbine, meaning the density of a wind turbine as a function of, or as a unit of area. Okay, and we refer to this as the power density right now. This density here, it can also be written out as pressure over RT, which is just the gas constant, and then T being the what? The temperature. And this over here is what it is that we were actually trying to figure out. The power density of a wind turbine, okay, it is a function of the pressure, okay, it is a function of the speed, meaning it's directly proportional to the pressure, directly proportional to the speed cubed, okay, it's inversely proportional to temperature. Now, why is this important? Because temperature, it has an inverse correlation with our power density of our wind turbine. Okay? And this is just a means or a way of manipulating a few equations, understanding their significance or their importance in the context of a wind turbine. Obviously, these are not the final sets of or set of equations. This is just to whet your appetite, as to show you what's out there. Because what people don't realize is that this year it comes from your ideal gas laws this year. But because it has a pressure and a temperature component, it can now actually also play its way into the power density of a wind turbine. Imagine that. So yeah, that's where we will stop for now.